Hello everyone, welcome to my channel. This is John, and today let's talk about the number systems. In digital logic, we use a positional number system. In such a system, the magnitude of a number does not only depend on the value of the number itself, but also depends on where you put that number. For example, the decimal number system we use every day is a positional number system, right? We have 10 digits here, and we can use them to represent like any number. Just put those different digits in different order. Okay, so here I showed you a general format how to write a positional number. This is called positional notation. Here the R represent radix. So that's the base of the number system. For decimal, it's 10. For binary, it's 2. And also we have this point, it's called radix point. So in decimal, it's called decimal point. In binary, it's called binary point. And to the left of the radix point, we have the integer part. And for the to the right, we have the fractional part. Okay, and the leftmost bit here, which is n minus 1, we call it most significant bit, or just MSB. And the rightmost bit, in this case a minus m, we call it least significant bit, or LSB. So when the MSB changes, the value of the number changes a lot, but when the LSB changes, the value of the number changes a little bit. Okay. So those are some important terms about a positional number. And in today's world, the commonly used number system include decimal, binary, octal, and hexadecimal. Especially in the computer systems, we use the latter three, so binary, octal, and hexadecimal. But basically, the octal and hexadecimal is a different representation of binary. We will see this later. So whenever we wanted to learn a new number system, the first thing we wanted to know is how to count, right? So now let's try to count in different number systems. For decimal, no need to say, just write it down. So start from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But something we need to be aware is that because we only have 10 digits in decimal, so whenever we count to 9, in order to count the next number, we have to put a carrier to the next bit or next digit. So after 9, we have 1, 0. We read 10, right? Means it's it's larger than 9. Then we get 11, 12, 13, 14, 15, 16. However, in a binary system, because in a binary system we only have 2 digits, 0 and 1. So the way of representing is a little different. So let's see, starting from 0, 1. So after 1, we don't have any other digits to represent the number, so we have to move the position. So become 1, 0. So 1, 0 in binary actually represent 2 in decimal. Then we got 1, 1. This is 3. After 1, 1, we have to move to a higher bit. So we got 1, 0, 0 for 4, 1, 0, 1 for 5, 1, 1, 0 for 6, 1, 1, 1 for 7, 1 0 0 0 for 8, 1 0 0 1 for 9, 1 0 1 0 10, 1 0 1 1, 1 1 0 0 1 1 0 1, 1 1 1 0 1 1 1 1. So again, after we got 4 ones here, no other way to represent no other number allows us to use to represent 16, so we have to move to a higher place. So 16 will be represented as 1 0 0 0 0 in binary. Okay, so you got the idea. So whenever we reach to 1, for the next number we need to carry to the next bit. For octal, similar thing, but in octal we have 8 digits, so from 0 to 7. So we'll count 0 1 2 3 4 5 6 7. After 7 we have to carry to the next bit, so 1 0 1 1 1 2 1 3 1 4 1 5 1 6 1 7. Okay, then we become 2 0. Okay, so now you see like 1 0 in octal, so don't read 10, it's not 10, it's 1 0 corresponding to 8 in decimal. For hexadecimal, similar, but in this case we have 16 digits, so we start from 1 0 1 2 3 4 5 6 7 8 9 10. We don't need 10, actually we have a letter here, use A to represent 10, then B C D E F. After F, no more number to represent, so we have to carry to the next bit by 1. So after count to 15 we need carry to the higher bit. So 1 0 in hexadecimal corresponding to 16 in decimal. So that's how we count in different number systems. Okay, now we know how to count. Then let's talk about how to make conversions among different number systems. Let's start from the easy one. So convert from binary, octal, or hexadecimal to decimal. Okay, to do that, we need to know a special representation called polynomial notation of the positional number. So if you remember, this is general form for the positional number, and let's write it in the polynomial form. So we should know that each bit of this number has its own weight in the number system. The higher the bit, the higher the weight. So MSB has the highest weight and LSB has the lowest weight. And we can represent them as a n minus 1 multiply by putting the radix here, the r to the power of n minus 1, then plus a n minus 2 by r to the power of n minus 2, and we can keep doing this until we have a1 multiplied by r to the power of 1 plus a0 multiply r to the power of 0. Then after the radix point, we use similar way, so we need to continue to write, so plus a negative 1 by r to the power of negative 1 plus a negative 2 by r to the power of negative 2 until we reach the LSB, which is a negative m by r to the power of negative m. Okay, so this is the general format to write a number into the polynomial notation. Okay, so now let's use this to try out some of the numbers. First, let's try to write the decimal number in the polynomial notation. So that's 123.35 in decimal. So we write the radix here, so we know what number system is it. So following this, so here an minus 1 is 1, right? So 1 multiply radix is 10, the power n minus 1. So n equal to 3 here, n minus 1 equal to 2. So 1 by 10 to the power of 2 plus 2 by 10 to the power of 1 plus 3 by 10 to the power of 0 plus 3 by 10 to the power of negative 1. This 3 corresponding to this 3 here, to the left, to the right of the decimal point. Finally, the LSB 5 by 10 to the power of negative 2. So if you calculate this, add them together, you will get this number. So that's how we write decimal number in polynomial notation. Now let's check the other numbers. Say if I want to convert a binary number into decimal, what I do is write it in the polynomial notation. So we got, so here n still equal to 3, so we got first bit 1 MSB 1 by, now base, the radix is 2 to the power of n minus 1, so 2 to the power of 2 plus the next bit is 0 by 2 to the power of 1, the next bit is 1 plus 1 by 2 to the power of 0 plus 0 by 2 to the power of negative 1 plus 1 by 2 to the power of negative 2. So if we calculate this out, we got 4 plus 0 plus 1 plus 0 plus 1/4. So it's finally equal to 5.25. So that's the decimal value or decimal representation of this binary number. Similarly, the next one, 37.5. Now the base is 8. So here n equal to 2. So we start from the MSB 3 by radix, which is 8 to the power of n minus 1. So 1 here plus 7 by 8 to the power of 0 plus 5 by 8 to the power of negative 1. Now calculate and add everything together, we get 31.625 in decimal. Okay. Now last one, AE.5 in hex. Again, similar way. So we write A, we know A actually equal to 10. So we write 10 multiplied by the radix, which is 16 to the power of 1, because n equal to 2 here. And plus E. E is actually 14. So multiply by the radix 16 to the power of 0 plus 5 by 16 to the power of negative 1. Again, calculate it and add everything. We got 174.3125. That's it. Decimal representation of AE.5 in hex. Now next, how to convert from decimal back to binary. There are actually two ways to do this. The first way is called repeated division by 2 method. So again, I'll use an example to show you how this works. So say we have a decimal number 18. I want to convert to a binary representation. So use way 1. So what we will do is first we use 18 to divide it by the radix 2 here. So the quotient will equal to 9, and then there will be no remainder. Remainder is 0. Then we will use this 9 to divide by 2 again. So we get quotient equal to 4, and the remainder is 1. Then divide again. 2, we got quotient to be quotient equal to 2, remainder 0. Divide again. Now I got 1, remainder 0. Then divide again. Now this time the quotient equal to 0 and the remainder is 1. So we will stop the division when the quotient is 0. Okay. Then what we do is read our remainder from bottom up. Okay. So in this case we got 1 0 0 1 0. That's the representation for 18 in binary. Okay. For any decimal number, we can use this way to convert it to binary. But there is another way to do it. So way 2 is called sum of weight. What we do in this way is that first we write the power of 2. So to 2 powers, because this 18 is an integer number, so we just starting from 0. So to the power of 1, to the power of 2, to the power of 3, to the power of 4, to the power of 5. 5, I think that's enough. If we put the value here, we got 1, 2, 4, 8, 16, 32. Okay. So the higher the weight, the bigger the value, right? So now what we do is we first try to find those from those numbers, find the one that is closest to 18 but not greater than it. Guess what? That's 16, right? Then we put this bit, we put the corresponding bit 1 to be 1. Okay. Then what we do is we use 18 minus the value corresponding to this bit, which is 16, and we get the difference of 2. Okay. Then next step, we do it again. We try to find from those different values to find the one which is closest to 2 but not greater than it. Naturally, we will find this bit here, right? Then we put 1 here. Okay, then we use this difference 2 minus this value 2 here, we get 0. So once we get 0, we can stop and fill the other bit with 0. So again, we got same representation for 18 in binary. Sorry, not 18. 2 here. Okay, so that's how you convert from decimal to binary. To convert from decimal to octal, we use similar method as the binary case. So it's called repeated division by 8. Basically, we use this number, decimal number, divided by the radix, which is octal here, so 8. So if we do that, we got 2 here, 16. I got 23 here, and the remainder is 1. Then I divide it again, so I got 2, and the remainder is 7. Then I divide it again. Now I got 0 as quotient, and the remainder is 2. Then we stop here and write it back from bottom up. So we got 271 as the octal representation of 185. Okay. From decimal to hexadecimal, similar way. So we use the decimal number we wanted to convert, divided it by the radix. Now it's 16. So we got 1, 1, and the remainder is 9. Then we divide by 16 again. So we got a 0, and the remainder is 11. And we should know that 11, we represent 11 using letter B in hexadecimal number system, right? So then we read back, so I got B9 is the hex representation of 185. Now let's look at the conversion between hexadecimal and binary. As I stated before, the hexadecimal basically is a more clear way to represent the binary number, long binary number. Because if we have a very long binary number, it's get hard to read and easy to make mistake when handle it. So it's easier to read and to handle if we change it to hexadecimal. If you remember the table I showed you before, like how we count, we can see that actually each hexadecimal number can be represented using a 4-bit binary. Then in order to convert from binary to hex, what we do is first we will split the binary number by every 4-bit from right to left, basically from the LSB to MSB. Okay, so starting from this bit, so count by 4, 1, 2, 3, 4. Then we cut it, 1, 2, 3, 4, split it. Okay, then we convert the 4-bit binary into one hex digit. So 0116 0. If you check the table before, this corresponding to 6 in hex. 1110 corresponding to E. 110 only has 3 bits here, but we can add a 0 okay, to the left of it. It won't change the value of the number, but make it 4-bit. So this is still a 6. So the hexadecimal representation of this binary number is 6E6. Okay, and from hex to binary, similar thing, but just do the opposite way. This time we represent the hex number, so let's directly use this one. So each hexadecimal number will be converted to a 4-bit binary number. So E, we will get 1110. F, we will get 1111. 3, we will get 0011. It has to be 4 bits, be careful. So we add a 0 before it. B is 1011. So the binary representation of this hex number is this. Okay. The conversion between binary and octal is pretty similar, but the difference is that we only need a 3-bit binary number to represent octal, because the largest octal number is 7, right? We only need a 3-bit. So this time, in order to convert from binary to octal, we cut the number every 3-bit instead. Okay, then we convert every 3-bit to an octal number. So 011, 3, 001, 1, 101, 5, 111, 7, 111, 7. Okay, so the octal representation of this binary equal to 775113. Okay. Now let's try to practice a little bit. So let's convert this binary to octal similarly. So we'll first write this number down. Okay, then we need to cut it every 3-bit. If there's only 2 or 1 bit, we add 0 to make it 3. Okay, so 110, we got 6, 100, we got 4, 011, 3, 011, 3. So the octal representation 3346 in this case. Now B, from octal to binary. That's also easy. So just rewrite every bit into a 3-bit binary. So 7 we have 1 1 1, 6 we have 1 1 0, 3 we have 0 1 1. Okay, so that's a binary representation. About from octal to hex or hex to octal, there are ways to make direct conversion, but to me, I think either way that you can first convert octal to binary, then from binary to hex, or you do the reverse. Okay, if you noticed before when I talk about conversion from decimal to binary, octal, hexadecimal, I only give integer number or whole numbers. What about mixed number or fraction number? So I will use an example to explain. So in order to do that, we need to separate the whole part and the fraction part. For the whole part, we make the conversion using the way we already know. For example, if I want to convert this number to binary first, for the whole part, I use repeated division of 2. Like 1, 2, 2, 0, 2, 1, 0, divided by 2 again, so I got a 0 and the remainder 1. Then I read, so the whole number 9 is 1001 in binary. Okay, but how about the fraction part? To convert to the fraction part, we need to use a different way, which is called radix multiply method. So this is opposite as the repeated division. Actually, we are doing repeated multiplication. So how we do it? So first, we only take the fraction part, which is 0.95. Then we multiply it by the radix, which is 2. And this gives us 1.9. Okay. Now we just take out the whole part, then use the fraction part, then 0.9, multiply it by 2 again, so we get 1.8. Again, take out ignore the whole part, the whole number, just take the fraction. So we got 1.6. Do the same. So we got 0.6 by 2. We got 1.2. Do it again. So 0.2 by 2. We got 0.4. Then since the whole part is 0, then we just do 0.4 by 2. We got 0.8. Then 0.8 by 2, we got 1.6. So up to this point, probably we found something that if I keep doing the multiplication, we found that this number will repeat itself, right? We keep doing that. So which means if we convert this 0.95 to binary, it's gonna be an indefinite number, okay? Indefinite fraction. Okay. But how to write the result? So basically, we just write the whole number we get in sequence, but this time top down. So we read 1111001. So 9.95 in decimal should equal to 1001. This is the whole number, the whole part, and then the radix point. Then we write 11110. Actually, starting for the next bit, it's going to repeat itself. So we can put a line here, mean this part is repeating. Okay. Now to the octal, we can also use the radix multiple method. Since we already got the binary representation here, we can direct convert it to the octal and hexadecimal number from what we learned before, right? So to octal, let's first write this binary representation here. Yeah, I just wanted to show you how to convert from binary to octal for fraction numbers, basically. And then let's repeat this a couple more times. So yeah, we know this will keep repeating itself over and over again, right? So we don't have too much, just enough that we can find how it repeats in octal and hexadecimal. So for octal, we know that for the whole part, we split the number every 3 bits, starting from right to left, right? So starting here. So 1001 in octal becomes 11 actually. Then we got the radix point. Now for the fraction part, we still cut the number every 3 bits, but this time we're starting from the higher bit. So starting from left to right. So we need to cut here, cut here, cut here, cut here, like this. So let's see. So 111 we got 7, 100 we got 4, 110 we got 6, 011 we got 3, 001 we got 1, 100 we got 4, 110 we got 6. So even though I didn't write everything, but I can add 2 bits here, so got 3. So what do we find? 4631 is going to repeat, right? So basically we don't need this part. So what we know is this 4 will start repeating itself. So that's the octal representation. Finally, the hex. Similarly, let's write the binary here and then let it repeat for a couple of times. I think that should be enough. So 1001 in hexadecimal is still 9. Then in this case, for fraction number, we still cut the number by every 4 bits, but again, starting from left this time. So cut here, cut here. So we got a 1111, which is F. 0011, we got 3. 0011, we got 3. So actually, we already found, right? So 3 will repeat itself forever. So the hexadecimal representation will be 9.F3, and 3 will repeat. Okay, that's for the number system. If you found my video is helpful, please help like, share, and subscribe. And thank you. See you next time.